Professor Sinai, first of all, we would like to express our warm congratulations. You have been selected as the 12th winner of the Abel Prize, and you will receive this prize tomorrow. So let's go a bit back in history. You were born in Moscow in 1935 into a family of scientists. Your parents were biologists, I believe, and you had a grandfather who was an eminent mathematician. So we suppose that this had some important consequences for the development of your interests, of your skills, of your flavors. Is that right?
Definitely yes. How can I say no to this question? But it was not so direct as you think. I just participating in many Olympiads during my school years, but I never had any success, never won any award. So the purpose of this information is for young people who don't have just anything from this early Olympiad, so it might happen that it will be compensated in the future. Right, and then my grandfather was already of rather just big age, so he actually did not have enough energy to push me to mathematics. And I had just also half brother Barin blood, and he was at that time just in Moscow State University, and he was always convinced that I must go to mathematics. So under his influence, it probably happened that I decided to go to mathematics.
And do you still know when you found out that you had an exceptional talent for mathematics? Is there a particular moment or?
It happened very late. I even not so much sure even now that I have it. Yeah, there were no just real, just true signs that I am especially gifted.
But let's go back to schooling. You must have entered school around the time when Nazi Germany invaded Russia, and that must have had a lot of influence concerning your first years at school.
I just entered the school in '43. After our family returned back after the evacuation. So before that, there was just a life in Moscow was different. For example, it was forbidden to have windows in the apartment of Moscow to be just open, so it has to be dark. In '43, it was already allowed to have windows open, so it was a very big change. And after that, no just clear signs of the war was in Moscow. But certainly the life was very difficult, especially because it was still Stalin's time. And then just people had to behave in a very special way, and this was the influence of this just situation which was above everybody at that time.
And how did that show up in school?
Well, yeah, everywhere. For example, if you say some just non-traditional story, traditional words, you can be expelled from the school or even can go to prison.
Would you tell us a little bit about some teachers who had a special influence on you, maybe in particular concerning mathematics?
In our school we had a very good teacher of mathematics. His name was Vasily Alexeyevich Yefremov. He was a very good school teacher of old style. He always brought to us his problems written by his very accurate handwriting on a piece of paper and distributed it among his students. And because of so well just organized work, mathematics, was very popular among the students. So we always were trying to solve his problems, were discussing and all that. I just must say that it was not so at that time that I was the best in the class. There were young people who were definitely much better than me.
At what age was that, more or less?
Maybe 16, 17 years old.
So just before you entered university?
Yes, yeah, when I was still in high school.
Yeah. So we read that you entered Moscow State University in 1952?
Yes.
Still as a teenager then?
Yes.
Yes. And that was the Faculty of Mathematics and Mechanics?
Yes.
A very famous institution. So how was it to study at such an institution, say, as a young student?
We had some number of very good professors there. For example, the lecture course in analysis was given by Lavrentiev, by academician Lavrentiev, who was very famous scientist at that time. He just was involved in just very big administrative work, but also was a very good teacher, so his lecture course was very interesting. Then we had a very good lecturer in classical mechanics. His name was Chitaev, and his lectures were also very much interesting. I even was his student for 1 year when I was a student of the second year. Then initially we had the lecture course by Dynkin on algebra, and Dynkin was an excellent teacher for students of the first 2 years. So it was very, there were lecture courses of very high level. And then there was a lecture course by Bakhvalov. Yes, he was very well known in Russia, maybe not so well known in the West, but just there was a following story. We entered the university on the 1st of September, and the first lecture by Bakhvalov. He entered the room and said, "So let's continue." This was the beginning of his lecture course.
So to what extent were mathematics on one side and mechanics on the other side integrated in the curriculum? Was that important also for you later on?
First of all, these were more or less independent part of the Mekh, as you say. And but people could attend lecture courses on each part. So just I was just somehow attending some lecture courses there on also in physics, but not very much. So mostly I was in mathematics department, but also with some just addition of physics and mechanics.
So you told us already about some of your teachers, among them Rokhlin, apparently, and Dynkin. So let's continue with some of the other teachers that you met on later on after Dynkin. And I imagine that Kolmogorov must be very important for you, and maybe also Israel Gelfand. And whom else would you like to mention and to characterize?
Well, let's begin with Kolmogorov, because I became his student. So I was a student of Dynkin during the second and the third year in Moscow University, and I wrote my first paper under his supervision. I just solved the problem which he formulated for me, and it was a very interesting problem. Just I like what I did at this time, even until now. But then Dynkin...
That was in the beginning of your 20s, right?
Yeah, something like that. But Dynkin wanted me very much to work on the problem of Markov processes and the style of failure. The papers by failure became very popular in Moscow at that time. And so Dynkin thought that I should just continue this line. But I was not very much excited and interested in this. And so Kolmogorov organized a seminar, which initially was seminar on random processes and later became a seminar on dynamical systems and ergodic theory. And I just began to attend the seminar, and later I became a student of Kolmogorov. At that time he also was interested in problems of entropy of different compacts in functional spaces. So these were just the problems which we were discussing at that time.
But you told us that you Gelfand also tried to recruit you as your graduate student.
Yeah, this was a very concrete story. It was, if I remember correctly, something like in '55, and it was time when Gelfand was writing a famous volume of his books on distributions. At that time, Gelfand also was interested in probability theory somehow, and he just wanted me to that I became his student, and we had some discussion. And I told to Gelfand that I want very much to work on problems related to probability theory, because I already had this paper written under the supervision of Dynkin. And he asked me, how do I want to have probability theory, as an appetizer or as a dessert? And I said that I want to have it as an appetizer. And that was the end of the story. But it does not mean that our contact with Gelfand stopped. We met many times together, especially when Gelfand worked on some problem of representation theory, which were connected with some problems in ergodic theory, the theory of Fourier cycle on that, and we were discussing this question many times. So I attended his seminar for many years, because Gelfand had a remarkable just quality. He could explain different topics in mathematics in a very simple and clear way.
Mm-hmm. How about Rokhlin, your connection to Rokhlin?
So the story of connection with Rokhlin started after Kolmogorov's paper on entropy appeared. At that time, Rokhlin lived in Kolomna, which is a small town not far from Moscow. And at that time, he had just graduate student whose name was Abramov. And there are several theorems which just were proven by Abramov, like entropy of special flows and other things, Abramov formula and all that. And so when Rokhlin heard about the paper of Kolmogorov, he sent Abramov to Moscow to find out what was done, what is the situation, and is it possible to see the text, all that. So Abramov came to Moscow, and he found me, and we talked a lot about this. I told him everything what I knew at that time. And so Abramov just invited me to come to Kolomna and to talk to Rokhlin. And this is what I did. So I remember very well my first visit to Kolomna. So Kolomna is very just deep province in Russia. But Rokhlin had an apartment there, and my first impression there was about a person who was very well dressed. Everything in his apartment was very accurate, just very well ordered. So it was like just a very good, say, apartment in the center of Moscow, something like this. And we started to talk. And then Rokhlin had a very big experience in ergodic theory, because he published already several papers before that, and actually his doctoral thesis was on ergodic theory. And so Rokhlin formulated some number of interesting problems of ergodic theory. Some of them were connected with Rokhlin's theorem theory of measurable partition, which became a very useful theory in ergodic theory, and because of that theory, I could understand much better conditional probabilities in probability theory. And then just one of the problems which I started to work on under the influence of Rokhlin is the calculation of the entropy for the group automorphism of the two-dimensional torus. At that time, it was not known that Kolmogorov definition had to be modified, and so all the analysis was rather difficult, and I could not do anything. But then I just visited Kolmogorov, showed him my drawings, all that, and he said that it is clear that in this case the entropy must be positive. But even at that time, there was no question about publication of my paper, because there was just Kolmogorov papers of entropy, and it was not clear why another definition of the entropy is needed. And then, after some time, Rokhlin proposed his result about this definition by Kolmogorov, and then it became clear that I must publish my paper with the definition, and then with about the calculation of the entropy for the automorphism, which was done, or which was already done at that time. So that was the beginning of my contact with Rokhlin. After that, Rokhlin was organizing a seminar on ergodic theory in Moscow, which was attended by such people like Arnol'd, Anosov, maybe some others, and this seminar was Alexeyev, and this seminar was in parallel with his seminar on topology, where the central figure was Novikov.
Mm-hmm. We sort of are jumping a little ahead now. Could you, in very broad term, for a very general audience, explain what is a dynamical system? How does it appear in physics, for instance?
No, we understand it that we understand dynamical systems as objects which describe all types of evolution. And the most interesting case is a nonlinear dynamical system, where the equation of dynamics of evolutions are nonlinear, because there can be many different phenomena which deserve some deep studies.
And what is an ergodic system among these dynamical systems? What is an ergodic system?
Yeah, I just have the following very good example of ergodic system, which I always give to my students. Suppose that you want to buy a pair of shoes, and suppose that you live in a house which has a store for the shoes. Then there can be two different strategies. One strategy is that you go to this store every day, and check the shoes which are there and find the best one. Another strategy is the following, that you take a car and go to all food stores in the town and find the place where you see the best shoes, which you buy immediately. So the system is ergodic if the results of both strategies are the same.
Very good, very good. Okay, so the ergodic theory, and of course, which came very naturally from, if you like, from physics. I mean, studying, Hamiltonian equations and so on. So, can you explain, also in general terms, what is now chaos? What is chaos in mathematical? How does one sort of measure chaos? What is it?
Well, it's the subject of my lecture, which will be the day after tomorrow, but I can tell you in a few words what is it. And the main question is, what is the difference between chaos theory and, say, probability theory? So, if you have probability theory, so you study coin tossing, and you can have experiments, say, of 100 coin tossing, and you can have many series of these experiments and can just study their results. But if you consider the problem of chaos, then, for example, if you want to measure the temperature at some point, then you will make this measurement during 1 year, and then you will have only one realization of the temperature. You cannot have 100 or 1,000 realization of the temperature in a given place and given time. So the theory of chaos studies, first of all, the question when the series of measurements have a limit as time tends to infinity, and how to describe these limits. Yeah. So the existence of the limit actually follows from some hypothesis, which follows from the equation of motions, which give the existence of the distribution which determines the value of all kinds of just averages. Better to say, they just give the existence of these averages and also allow to find their values. And then the question is, what are the equation of motion which just determine this just distribution and these averages? And then the basic statement in the theory of chaos is the statement that the dynamics must be unstable. Instability means that small perturbation in the initial condition lead to just large perturbation in the dynamics after some time. And then there is just a mathematical theory which says that if the system is unstable, then time averages exist and gives a possibility to calculate this time averages. It's just a very just general description of what is done in chaos theory, and more precise description requires some conditions and just the forms of instability and other more just detailed things.
So this is what is said that very sensitive to the initial conditions, right? And also used as the butterfly motion in Brazil can cause a storm in the Caribbean or something like that.
This is another example.
So the next question is then, how do you measure chaos? I mean, I guess entropy comes into the picture here.
We understand under chaos just what I said before, the existence of time averages, their values, and also some object related to mixing. I did not explain what does it mean mixing. And then there are natural just evaluation of chaos in terms of the distribution. Yeah. The entropy is just used in the theory of unstable systems, system with instability. And it somehow just characterizes how many types of dynamics can be in a given system. And certainly it is just a very useful notion because just the positivity of entropy just determines other property of the system which can be described, but it's more technical question.
You just mentioned, I mean, with the way you described with Rokhlin, that Kolmogorov, of course, had come up with a definition of entropy for Bernoulli shifts.
Yes.
But then he changed it when he wrote down the thing, and that definition was not invariant. And then, of course, you came with the correct definition of entropy. Isn't that correct?
Yeah, that's correct, yes.
Yeah, and what is now in the literature called the Kolmogorov-Sinai theorem is, of course, an efficient way to compute the entropy.
Yeah, that was just the definition which was not used by Kolmogorov, but just required a little bit the modification which I proposed.
Yes, and now you came up with an extremely interesting example of an ergodic motion, namely the so-called billiard.
Mm-hmm.
And could you just describe again in general terms what is a billiard?
You know, billiard is just, as people know, is the motion of a ball inside a billiard table. The mathematical theory just appears if you allow billiard table to have more or less arbitrary form. And then there is just a natural question which actually was raised by a Russian physicist Krylov much before the theory of chaos appeared. What are billiard systems which have the same instability as particles moving in the spaces of negative curvature, which are just the best example of unstable systems. Mm-hmm. And then this theory of billiards says that if the boundary of billiards is concave, then the corresponding billiard is unstable in the sense of previous description which we had before, which shows that if you consider two initial conditions with different value of the velocity, then the corresponding trajectory just diverge exponentially. But apart of that, you can say the following, that if you consider as a typical example of this unstable billiard the square from which just a circle is removed, then the difference between this billiard and the usual billiard is that for unstable billiard, the particle comes to the hole, the move, much faster than for the regular billiard.
I see, okay, I see. Yeah. This becomes, of course, a little technical, but you proved a very, very important result about if you have a system with positive entropy, you can find actually a Bernoulli shift, which is what is called a factor with the same entropy. Yeah. And this implies that you have between two Bernoulli shifts with the same entropy, they are what is called weak isomorphic.
Yes.
And of course later Ornstein proved the result that the entropies are complete invariant.
Yes.
But it follows from the work, I guess, by Ornstein that the billiard example is in a sense the most chaotic system one can have, because it is actually a Bernoulli flow, right?
Yeah. So it just from Ornstein's theorem, it follows that if we have two billiard systems with the same value of the entropy, then they are isomorphic.
That's a remarkable result.
It's a remarkable, it's a great result.
Yeah, and of course it also does, the coin tossing thing is in a sense similar to this deterministic billiard thing, which is completely amazing. Mm-hmm.
My result says the following, that if you have a system with positive entropy, then there can be a subsystem which moves like Bernoulli shift. Or just
yeah. What about higher dimension, about billiards in higher dimension, that 2 dimension? Is there something known about these?
Oh, a lot of things are known. Just, for example, there are the results of Hungarian mathematician Nandi Shimani, who is in Atlanta, I think, where he just studied multidimensional dynamical systems, which eventually become unstable systems, have positive entropy and are ergodic.
Mm-hmm. Mm-hmm. You also, and this of course is your joint work later with Ruelle and Bowen, you introduced Markov partitions of, and of course this led to what later became, I guess it's called Sinai-Ruelle Bowen measure. Could you explain a little about that?
Yeah, first of all, the story was the following. First, there was my paper where I just constructed these measures for the case of so-called Anosov systems, or just hyperbolic system. Then there was a paper by Bowen and Ruelle in which they just extended this construction to systems considered, say, by Smale, axiom A, systems which have hyperbolic behavior. And so these measures are important if you study irreversible process in this system. So suppose that you start from some non-equilibrium distribution, and then you consider the evolution, and you ask how non-equilibrium system converges to the equilibrium distribution. And the result of this theory says the following, that this evolution, in a sense, is very non-uniform. Along some direction, this is just very small evolution, just so that all just time averages behave very well and converge to a limit. But along other direction, this convergence is very erratic and can be studied only using probability theory and all that. So these measures, which are called SRB measures, are the measures which are smooth along some just unstable directions and are very irregular along the other directions. And this is a class of measures which appears in the theory of evolution of even smooth distributions.
And this is related to the so-called Gibbs measure also, isn't it, in a sense?
Yeah, these measures are examples of Gibbs measures, but Gibbs measures are much more general.
Right, right.
Let's go back to a more general platform, comparing mathematics and physics. So I'd like to start with a quotation from the physicist Eugene Wigner in 1960. I think he published a paper called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, where he somehow gave lots of examples showing that mathematical formalism somehow really advanced physical theory and made computations possible and so on, to an extent that was almost ununderstandable. Have you experiences that somehow underpin his quotation?
Well, just my impression is that this effectiveness of mathematics now does not surprise people. There are so many cases, and even these things which you find in string theory, all this, which is just practically mathematical theory for physics somehow. So there was just some time ago, Joel Leibowitz, whom you maybe know from, he organized whole discussion about this phrase by Wigner, and different people expressed their opinion, how can it be that mathematics is so effective, and just the conclusion was, I understand, that it's somehow just well-established fact that this is so.
Mm-hmm. On the other hand, there seems also to be a move in the opposite direction. I mean, if I understand it correctly, then physicists have had quite a lot of impact on questions in quantum geometry on the one side, sometimes even in number theory, where they came up with formalisms that were not really well developed mathematically, but on the other hand, they came forward with correct assumptions or correct predictions, I would say, that then only after a lot of mathematical development could be shown to be true. So there is something that also goes the other direction. Is that right?
So it is effectivity of mathematics, but you can say that it's not enough effective.
Mm-hmm. You yourself had a paper maybe 10 years ago with a title, Mathematicians and Physicists is Equal to Cats and Dogs, I think written with a twinkle in the eye. So what is the main message from that paper?
That I wanted to show the examples where just mathematicians and physicists look differently on the same problems. And so one example of that was the following story, that my student Pirogov and I worked on some problems in the theory of phase transitions in statistical physics. And we proved some theorems, and I went to meet very famous physicist in Russia, Ilya Lifshitz, who replaced Landau when Landau had his accident, and wanted to show him just our theory. But, and then I started to show everything, but then just he stopped me and said, it is very trivial, just very simple. What are you talking about? And he just started to write some formulas, which eventually just gave our results. And I just left him very much embarrassed, and I started to think why did this happen. And then I realized following things, that the fact which was the final result of our theory was for him just something like an obvious statement. He certainly did not know how to prove it, but he did not need the proof of it. He just used it as self-obvious fact.
You know, there is a famous citation by the great Gauss, who once said, now I have the result. The only thing remaining is the proof. So there is also an intuition in mathematics, you know.
Now, there was also some story again connected with Gelfand. Just once we were talking with Gelfand, and we explained him one theorem, some result which we obtained together with Minlos, maybe you had his name. And Gelfand said, that is obvious, just all physicists know this. And then we asked him, if it is obvious, should we write a text of 200 pages with complete proof? He said, looked at us and said, certainly yes.
I would like to come back a little bit to sort of political types of questions. So you mentioned already that being at school in Stalin time was not always easy, but also later on, when you entered university and started your career, I mean, we suppose that, maybe that was not mentioned, but you come from a Jewish family, and in the Soviet Union, at least for times, there was a latent anti-Semitism. So that has probably been not so easy to enter the system and make a career. Could you comment on?
Well, there were just, I want to mention three just cases in my career which were connected with anti-Semitism, which you mentioned. The first one was just the entrance examination, which I failed for the first time, and then the influence of my grandfather, who was the head of the chair of differential geometry, the influence of my grandfather required, in order to just give me a possibility to have another exam and to pass the entrance examination. But this was a clear sign that everything was not so simple. Then the other case was with my entrance examination to the graduate school. Yeah, it was the examination in the history of the party, and I was always very bad in this field. And so just when I failed during the exam. There were some, I don't want to discuss the details, but just it was clear that some people could have better grades than the others. And then Kolmogorov and Alexandrov. Alexandrov was the head of mathematics department of Moscow University, just visited the head of the chair of the history of the party and asked her to allow me to have just another attempt. And then she just gave the permission, and I had the second attempt, which gave me B, but B was enough to enter the credit school. But it certainly, the result a priori was not clear. It could happen different way. And then the last case which I want to mention was the following, that you probably know about the letter in support of Yesenin Volpin, yes, which was signed by something like 100 mathematicians, and because of that, the possibilities of many of them has been changed. And for example, I could not travel abroad anywhere after that for 17 years, and just at that time I applied for a position of full professor at Moscow University, but I also was denied, and I became a full professor only 17 years later. So that was another example of the events which has happened at that time.
But in spite of these obstructions, it's quite obvious when you leaf through the number of famous Russian mathematicians that a lot of them have a Jewish origin in their families. And this is quite amazing that there are so many of them. Can you offer any explanation for that fact?
Well, maybe I shall say something trivial. First of all, Jews had some tradition of more learning than other nations. They learned Torah and just other religion book, and they spent a lot of time on doing this. So young people, Jewish tradition, could study better than other people. Yeah. And the other thing was just at that time, just to follow Jewish religion was very strictly forbidden. So people could do it somehow under very high pressure, in the sense that what they were doing very much forbidden. But if you do something under the pressure, then you work more, because there is some conservation law. And this is why just Jews could have some success.
And you always had to be better, really much better than the other in competitions and so on, which also sort of probably promoted this.
I think it will be wrong to say that we had this feeling. We certainly tried to prepare to all exams, to all competition. Yes. The result was not clear a priori, but there was always hope that something will come out.
But the other thing, which is more general, is in the Soviet period, especially in the Stalin, but also later, I guess a lot of very intelligent people were attracted to sciences, because in science, let's say then physics or mathematics, you didn't have this restraint that you would have in history or political science, or all these things. Isn't that true?
Yeah, that's certainly true. Yeah. So well, let me just give you one example. So at that time, there was a following rule. So Moscow, Mekh had many students who came as a graduate student from other countries. But there was the following rule, that only they can have advisors, or they can have only advisors who are members of the party. But there were students who wanted to work with Arnol'd, with me, maybe with other people. So the way out of the situation was the following, that there was some number of, so to speak, honest people. And the student became had the advisor, these just members of the party, but worked with just professors, with mathematicians who were not. Okay. Yeah, that was the way out of this.
Okay. You mentioned Arnol'd, and we talked about Arnol'd. Of course, he died 4 years ago. A brilliant, absolutely brilliant Russian mathematician. And you both followed Kolmogorov's course in 1958, maybe. Kolmogorov gave his seminar talk. And of course, Arnol'd went on with the so-called KAM, Kolmogorov-Arnol'd-Moser theorem. But you mentioned that you and Arnol'd, they were on your grandfather's side. There was a friendship. So But then you both loved outdoor and hiking. And once you went to the Caucasus Mountains, and you have to tell us this when you stayed in the tent for these shepherds. You have to tell that story.
I can tell you this story. It's just very funny. So just the weather was very bad, a lot of rain, and so it just we came to the shepherd's just tent, something like this, to spend there the time, and then just they allowed us to enter, and then our clothes became dry. It was very good. But then we decided, then we just understood that we lost our tent in mountains, so we decided to return back and to find it. And so we started to walk back, and these shepherds had very big dogs. Yeah, these are called Caucasus just dogs. It's just very big, very just angry. And so the shepherds left, and the dogs just found out that we were leaving, and they just surrounded us and started to bark very much on us. And then just the following has happened. Arnol'd started to cry on them with all the obscenity which he knew. And then just it turned out that the dogs did not touch him. But I was staying nearby with my trousers, and they just tried, and they just teared my trousers very much. They just practically did not touch my skin, but just the trousers. But then the shepherds came back, and we were saved. That was the story.
Okay. Going back to relations between East and West that we already touched a little bit upon, you told us that you were not allowed to travel for quite some time, and that happened for a lot of Russian mathematicians at the time. So would you say that that really hampered progress in science at the time, or was it just a delay, or was it just had it just have the effect that Russian mathematics didn't get the recognition in the West that it actually deserved? How would you evaluate the situation?
Not your question. It's very difficult to answer your question, because you are asking what will happen if something does not happen.
That's right.
Yeah. So we know what has happened as a result of all this delay and all this event. How can we say what would be the result if the development will go in different way? It's just impossible to say. Certainly it will be some harm, but how big is just will it be? It's not clear.
But on the other hand, I know that Arnol'd especially was rather aggressive about that. I guess it had something to do with bad communication between East and West. That's something that was discovered in Russia during this isolation, if you like, was much later discovered in the West. So the Russian mathematicians didn't get the recognition they deserved.
Well, I just have a very special point of view on that.
Okay.
That it's the question is about whether some result can be stolen. Yeah. So my point of view, with which probably many people don't agree, is the following: if the result can be stolen, then it's not a very good result.
Okay, that's probably true. That's probably true.
Getting back to yourself, you moved, in fact, in '93, I believe, from the Landau Institute for Theoretical Physics of the Russian Academy of Sciences to Princeton University, while still maintaining your position at the Landau Institute. Why was it so attractive for you to go to the United States?
You know, that is an easy question. First of all, I had many friends in Princeton, and just when we met, we always just had many points for discussion and common interests. Then just this was one reason. another reason was certainly that condition that many people from Russia just escaped. So the situation there was not similar to what we had before. That at the previous time, all people were in Moscow or just in St. Petersburg, and you could call to everybody and ask questions and have some discussion. Now it just became impossible. Yeah, and then that's what I already mentioned, that the conditions for the work in the West, in particular in Princeton, were much better.
So now I've been in the United States at least part of the time for more than 20 years. So you must know the American education system almost as good as the Russian one. Could you tell us a little bit how they compare to each other? I mean, seen from the point of view as a teacher, as a student, work conditions, atmosphere, and so on.
This is just very general question, which in a sense requires a very long discussion. So I can tell you a little bit what I don't like in the American system. But people will be very angry on me. That I don't like the system of just recommendation letters, because just the way how people write it and the way how they are considered does not often shows the real quality of a person who just applies. And so we have many examples when we accept students who later become not so strong and so gifted. Yeah. Then this is one thing. Another thing, then, it's certainly very much related. So, for example, when just we have young people who apply, then if it is in Russia and if a person has some number of publications, then it will be considered as a very good sign. Yeah. But in the United States, people usually think that publications of the graduate student were done under big influence of his advisor, his or her advisor, which is not always the case. So just it seems to me that in the American system, people must pay more attention to the individual results of the student.
One question about you as a teacher. You have been teaching courses and seminars and so on for almost your entire career. Do you have a particular technique, a particular philosophy, for example, posing a lot of problems, as you told us about some of your teachers? Or do you do it differently?
You know, first of all, I like very much to teach undergraduate courses compared to graduate. The reason is the following. When you teach undergraduate courses, you can easily see how your students become more clever, more educated, because they absorb new things, just new notions, new connections, all that. If you teach graduate courses, then usually it is just more narrow, just piece of work, when students are mostly interested in some special things which is needed for their thesis. And for me, it is just less attractive.
But nevertheless, you have an impressive list of students who have done well afterwards, I mean, graduating under your supervision. Just to mention one big name, Grigor Margulis, who won the Fields Medal, who will give one of the talks at the occasion you already talked about, and a long list of people.
Well, just I think the reason is exactly not in me, but in the problems in which we are working. I think just we do very interesting mathematics and we formulate very interesting problems, and so students are attracted by these problems. This is my explanation.
You are, of course, a very good example of mathematicians. They flourish in late age as well, because I came across that you published a paper this year on related to number theory. And you also have published other papers related to number theory. Yes. And you kept an interest in that aspect of, if you like, ergodic theory?
Yeah, definitely. Just I think that in this field which we are working, there are many problems which are just more natural for ergodic theory than for number theory. Yeah. I don't want to mention it, but just we had one paper which was very natural for people from ergodic theory than for number theory, so we could more easily to get the result.
But you mentioned that you've only published one paper with Kolmogorov, but you would like to have published more papers. Could you tell the story why you said something about Kolmogorov's sort of way of, yes?
So that was a story which I mentioned, that Kolmogorov at some moment decided that Russia, Soviet Union, did not have enough applied statistics. So he worked on just theoretical statistics and has many just beautiful and deep results. But he was not satisfied with the fact that these theorems of applied statistics were not used for practical just purposes. He found a problem, which was a problem related to the motion of the axis of rotation of the Earth, which can be studied with the help of mathematical statistics, and even French observatory publishes the information about the dynamics of this axis of rotation every 2 weeks, something like this. And Kolmogorov wanted very much to construct statistical criteria which can predict this motion. And he wanted us very much to work on this. And so he invited a very good geophysicist, Fedorov, who was one of the main experts in this. You're meaning this story, right? Yeah. And so just we were sitting there, and Fedorov was there, Kolmogorov was there, and Kolmogorov, showing at us, said, "Look at these people. They prefer to write a paper for Doklady." Doklady was one of the main journals there, than to do something useful.
But wasn't it also Kolmogorov said that he would spend 2 weeks at a problem?
Yeah, and also Kolmogorov just used to stress that he did not have papers on which he worked on the. He worked for a long time. Just mostly he prepared his paper, including the proofs and the text, in just 2 weeks. Yeah, and this was the difference in our style. Kolmogorov was very, as we say, a person with strong temperament. Just he could not do anything slowly.
Yeah. He was a towering figure, not only in Russian mathematics, but of course in the 20th century. He's ranked as one of the absolute greatest, yes.
Can I just tell you one more story about him? But it's slightly different. So once, when it was already when Kolmogorov was close to 80, maybe something like this, and I asked him, how did it happen that he was a pure mathematician, but worked on such just concrete physical problems as turbulence? Yeah. And he answered in the following way, that he was studying the results of concrete experiments. And so he had rulons, how you say that, a lot of papers with the result of experiments which were laying on his just floor, and he was studying all this result, comparing them with it. And after that, he came to his hypothesis in turbulence.
So in other words, you say that his intuition was motivated by physical considerations?
Yes. Yeah. And Kolmogorov subscribed to some journal, to some physical journals, and read them just so. He, in a sense, big part of Kolmogorov was in physics.
Is that also true for you, or are you, when you think about things, is it mainly in terms of algebraic, of analytic formulas, or is it geometric intuition, or is it a mixture of all of that?
It depends on the problem. Just I must come to the conclusion that there is a problem which must have an answer. Just I just told the story to just another journalist that once I had a problem in which I just knew that there should be some answer. And the problem was to find this answer. And I was working on this problem for 2 years. And at the end of this time, I discovered that this number is 1/2.
What about, have you had what we very often call the Poincare moment, that all of a sudden you see the proof? Maybe you worked on it in your unconsciousness. Do you have had such moments?
Yes, but yeah, I think this happened, but it just happened after maybe a long time or maybe years of very difficult work. So it was not like I was just trying to find a taxi, and when the taxi came, I had just this alert. No, it was very hard work for a long time. But then suddenly, at some moment, there can be just a moment when it becomes clear how the problem can be solved.
Well, unfortunately, I can see we have to come to an end by now. But I would like to ask one final question that has nothing to do with mathematics, at least not right away. You have certainly concentrated very much on this subject, but I'm sure you have also developed other interests. Maybe you could just give us a few words about what are you interested in, what are you keen on?
Well, just I was interested, especially in the previous years, in many just parts of sport. Yeah, I was very ardent just volleyball player. I liked very much to ski, downhill ski and cross-country ski, and then I liked very much to go to mountains. I cannot say that I was professional alpinist, but just I liked very much to go there. So on this conference there is a close friend of mine, Zakharov, who worked on integrable system, maybe you know that. And so we are close friends, and we were in mountains together, and there was a slope whose length was 300 meters. Yeah. But it took us 4 hours to go down.
So thank you very much for this most interesting conversation. And I would like to thank you on behalf of the Norwegian, the Danish, and the European Mathematical Society. Thank you.
Yeah. Thank you very much for everything, for the time which we spent together, and hope to see you again.
Thank you very much. Yeah. See you.